Good evening, everyone. I welcome you all on the behalf of Department of Mathematics, Wilson College Autonomous Mumbai. I welcome you all in the today's session. Our today's guest is Dr. Akshay Kumar sir. He is an assistant professor at Department of Mathematics, Vellore Institute of Technology, Amravati, Andhra Pradesh. He will deal with the topic of linear algebra today. Over to you, sir.
Okay, thank you for the introduction. Am I audible to everyone?
Yes,
Yes, sir,
sir.
audible.
Okay, thank you. So let me share my screen. Is my screen visible to you?
Yes, sir, visible. It is showing the eigenvalues written on the board.
Okay, okay, thank you. Okay, so today I will do the eigenvalues. So let me start with the definition of an eigenvalue. So most of the time we will focus on matrices. The reason is every linear operator is actually a matrix. So it's better to focus on matrices only. So what is an eigenvalue? Suppose you have a matrix A. We will only consider square matrix and order n cross n. So square matrix suppose you have, and what is an eigenvalue? So a scalar lambda is an eigenvalue of matrix A if Ax is equals to lambda x for some vector x which is non-zero. X should be non-zero. So if this happen, we say lambda is an eigenvalue for matrix A. And in this case, this x is called eigenvector corresponding to the eigenvalue lambda. Okay. Now let me give you one very simple example. Suppose you have an example like you take this matrix 1, 1 or maybe 2, comma 0. Okay. Now if you take x equals to 1, 1, then the matrix A is this one. So can you calculate what is AX? So it is just 1, 1, 2, 0, then 1, comma 1. So it will be so 2, 2. So 2, comma 2 you take as common. So 2 into 1, 1. So both these x are same. If you take lambda equals to 2. So 2 is an eigenvalue for the matrix A. Right. Now similarly, if you do for this matrix, if you take A, Y, and you take y equals to take 2, then it will be minus 1. So it has to, okay, we will do this later actually. So you can calculate the eigenvector for this also. So you can check when another eigenvalue for this will be minus 1. Right, we will do this later. Right, we will do all those things. So we need some tools to calculate these things. So this one is actually easy. So I have done this one. Now suppose you have a matrix A. So take general case. Why I have discussed this case here. So if you take general case, now if you see here, so what is the sum of this row? 2. Now what is the sum of this row? 2. So sum of all rows are same. So now suppose you have an n cross n matrix, right? And sum of R1 is say k, and sum of R2 is also k. sum of all rows is equals to k. Now if you take x equals to, the order is n cross n, so if you take n cross 1, 1 1 1 1, then if you multiply this ax, you will get k k k. So if you take k as common, you will get 1 1 1. So if sum of all rows are same and equals to k, then k will has to be an eigenvalue of a. Right. Now similarly, suppose you have a matrix A. Now in this case, now suppose the sum of all columns, suppose C1, C2, so on Cn, the sum of all columns is suppose k. Now in this case, what we can say? So in this case, if you take A transpose, so then what you can say, the sum of all rows, because here column will be converted to rows. So now sum will be k, sum of all rows will be k. Right. So what we can say from the previous thing, so k will be an eigenvalue of A transpose. Right. Now later we will prove that, we will see this A and A transpose both have same eigenvalues. We will do this. A and A transpose have same eigenvalues. So from this we can say k is again an eigenvalue for value of matrix A. If the sum of all rows are same and equals to k, then k has to be an eigenvalue of A. And similarly, if the sum of all columns is k, then k has to be an eigenvalue of A. Right? You can take different symbol if you want. So you can take R, R, R. Right? It doesn't make any difference. Okay. And corresponding to these, in this case, what will be the eigenvector? In this case, eigenvector will be this 1 1 1 1, right? But in this case, like for this case, eigenvector will be 1 1 1 1, but in this A case, eigenvector may be different. It may not be 1 1 1, it may be a different eigenvector. Okay. Now, so when since we are doing everything in linear algebra, so in the natural question you should ask here is, now suppose you collect all the vector v such that av equals to lambda v. Lambda is an eigenvalue of a. So lambda is an eigenvalue of a. So you take this e lambda, all the v vectors v such that av equals to lambda v, and you take e as all the eigenvectors corresponding to the eigenvalue lambda. Now can you tell me, are both e lambda and e same? Are both these two, a lambda and e, are same? Anyone?
Yes, I think.
Okay, let me open the.
No, sir.
No, this may be different. So why?
Because
Sir,
one eigenvector can correspond to only one eigenvalue. But in E, there are all eigenvectors.
But like suppose you have a V in EW E, right? So V is an eigenvector of the matrix A corresponding to lambda. So that means A V equals to lambda V, right? So it simply says E is always subset of E lambda, right? Now, can you do the converse thing also? No, both are not same actually. The only difference is in this collection E lambda, you have this 0, 0 vector also, right? If you take V equals to 0, then A of 0 is equals to 0 and lambda into 0 is also 0, right? So 0 is also belong to E lambda. But we have like in the definition we have said that 0 cannot be an eigenvector, right? We are choosing only non-zero vectors. So E lambda is just E union 0, right? Now the question is, since 0 does not belongs to this E, this does not belongs to E, so this cannot be a subspace. Uh, since all the vectors in E are n cross 1, so it is not an, so M n cross 1 matrices. Either you choose R or C, whatever you are taking. So it is not a subspace of M n cross 1 matrices, right? The question is whether E lambda is a subspace of, is E lambda a subspace of M n cross 1 matrices over R or over C? What can you say this about this? Is E lambda is a subspace?
Yes, sir. E lambda is a subspace.
Yeah, it is a subspace. So it will always form a subspace. E lambda is a subspace of M n cross 1. Or if you are doing everything on real field, or if you can take C also, if you are doing everything on complex field. Okay. Now, so since you have it is subspace, so what will be the dimension of this? Okay, till now we don't know the exact dimension of this, but it is always greater than equals to 1. It cannot be 0, right? Because lambda is an eigenvalue. For some x non-zero, we have ax equals to lambda x, right? So some non-zero vector is there in E lambda, so dimension cannot be 0. It is always greater than equals to 1, right? And it is always less than equals to n. So it will be between 1 and n, right? And this dimension is called geometric multiplicity of lambda. Okay, now, so let's come back to the definition of eigenvalue. So we said lambda is an eigenvalue of A if Ax equals to lambda x, right? And for some x non-zero, right? So can we write this A minus lambda I x equals to 0 for some x non-zero? Both are same thing, right?
Yes, sir.
So can't we write from the second statement? So the null space of A minus lambda I is not equals to 0. Both are same thing, 2 and 3,
Yes, sir.
right? So from 3 can't we write nullity of A minus lambda I is not equals to 0, or you can write greater than equals to 1, right? Because null space is not 0. And from the fourth one, can you write rank of A minus lambda I is,
Less than n.
since, so what is the order of A minus lambda I? It is n cross n matrix, right? So since nullity is not 0, so by rank nullity theorem, rank plus nullity equals to n. Nullity is not 0, so rank has to be strictly less than n, right? And which is equivalent to determinant of
A minus
A
lambda
minus
equal to 0.
lambda I equals to 0. So all these 6 statements are equivalent. So lambda, so the following are equivalent, right? Now if we take the particular case, now suppose we take lambda equals to 0, and we say, so what lambda equals to 0, so lambda equals to 0 is an eigenvalue of matrix A if and only if, so the first statement Ax equals to lambda x. So if you put lambda equals to 0, so Ax equals to 0 for some x non-zero. Now third statement will be nullity of null space of A is not equals to 0. Fourth statement is nullity of A is always greater than equals to 1. Then rank of A is always strictly less than n. 6. Determinant of A is 0. So all these statements are equivalent. Right, just put lambda equals to 0. These are this one is the special case of the above one. Just put x lambda equals to 0, right? So see how eigenvalues are related to many other things. Okay, now so from this, so this one, let me draw this. This statement is very important, very useful, very important and very useful. Now, so how to calculate eigenvalues? Now, suppose, now if lambda is an eigenvalue, then determinant of this A minus lambda I has to be 0. So what we can do, just calculate this polynomial. P lambda is equals to determinant of A minus lambda I. So it will be a polynomial of degree n. So it will be a polynomial of degree n, right? Now if, now if lambda is lambda, suppose you denote some, you take some other notation. Suppose mu is an eigenvalue of A, right? Then A minus mu I determinant has to be 0. So that implies P mu has to be 0, because both are same thing. So what are eigenvalues? Eigenvalues are just roots of this polynomial. just calculate this polynomial and find the roots. That will be your eigenvalues, right? And this polynomial has a particular name called characteristic polynomial. Right now, whenever you expand this determinant, so you will have lambda to the power n something minus something here, lambda to the power n minus 1, something like that, right? So the second thing will be sum of roots, right? So here you will have trace of a. So the from this characteristic polynomial, what you will get, the sum of all eigenvalues will be exactly equals to trace of a, right? Similarly, you will get the product of all eigenvalues is equals to determinant of a. Now let's come back to the first question. So this one, right? 1120. So we had this question, a equals to 1120. Now suppose now from this polynomial, now how many roots this polynomial have? Since the degree is n, so it can have only at exactly n roots. Now you need to be careful here, because you are using fundamental theorem of algebra here. It is a polynomial of degree n, right? You are saying exactly n roots. This is only applicable if you are allowing your lambda to be a complex number. If you are only looking for real eigenvalues, so this p lambda may not have any root. So okay, let me give you one example for this. Suppose you take this one, 0 minus 1 1 0. Now if you calculate a minus lambda I here, so it will be minus lambda minus 1 1 minus lambda. Okay, so it will be lambda square plus 1 equal. Now if this is the characteristic polynomial p lambda, if you put this polynomial equals to 0, so it will be lambda square plus 1 equals to 0. Now lambda square equals to minus 1, so lambda has to be plus minus iota. Although your matrix is real matrix, but still your all eigenvalues are complex. So this this is only applicable if you are allowing your lambda to be a complex number. If you are only looking for real eigenvalues, so a real matrix may not have any eigenvalue. So this is one of them example. So this is one of the example in which matrix is real, but it does not have any real eigenvalue. Okay. Now, so we were doing this question. So we calculated that. So how many eigenvalues this matrix have? Because order is 2 cross 2. The polynomial will be of degree 2. So exactly two roots this the polynomial have. So only exactly two eigenvalues we will get. So we already calculated one eigenvalue, that was 2. Now if we use this result, the sum of eigenvalues is trace of A. Product of all eigenvalues, determinant of A. Right. So lambda 1 plus lambda 2 is equals to trace of A. So trace is 1. Now determinant of A is, oh, we already know lambda 1. So lambda 1 is 2 plus lambda 2 equals to 1. So what is lambda 2? This is minus 1. So another eigenvalue is minus 1. Right. Now And suppose you have a matrix A. Suppose you have matrix A, and you calculated the characteristic polynomial P lambda, right? And this is an, suppose, n cross n matrix, and it will be a polynomial of degree n, right? And you have n roots, right? So it may happen that lambda 1 equals to lambda 2, or lambda 2 equals to lambda 3, right? So how many times lambda 1 is repeating, it is called algebraic multiplicity of lambda. So this means how many times lambda 1 is repeating in roots of characteristic polynomial. And you can verify that geometric multiplicity of any eigenvalue is always less than equals to algebraic multiplicity of lambda. Okay. Now, so suppose now you are saying, so if here by using fundamental theorem of algebra, we said every matrix has an eigenvalue if we are going for complex number, right? Now, so every matrix is an operator. Every operator, linear operator, is a matrix, right? So every n cross n matrix has an eigenvalue, right? If our field is complex number, we are allowing our eigenvalues to be complex number. Okay. Now the question is, suppose you have a linear operator. So this is just an operator from finite dimensional to finite dimensional, right? So this is actually an operator T from Rn to Rn. Every matrix is a operator. Now suppose you have a operator from X to X, right? But in this case, dimension of X is not finite, right? So can you say lambda, this T will always have a eigenvalue? Can you say T always have an eigenvalue? So answer is no. So suppose you take this example C01 to C01, continuous function from closed interval 01 to R, and you should define your linear operator as T of f equals to x into f. Then this linear operator, of course C01 is not finite dimensional, so this operator does not have any eigenvalue. Okay. Now let's see some special cases. Now suppose you have a triangular matrix, doesn't matter upper triangular or lower triangular. So suppose you have a11, a12, like that, a1 n and a22, a and n, and the below part is 0, right? Now what can you say about the eigenvalues of this matrix?
The diagonal element.
Okay, why? Why the eigenvalues are only diagonal entries? Now, if just to calculate a minus lambda I, so it will be a11 minus lambda a12 a1n. Similarly, these will be 0 0 a22 minus lambda 0 0 0. Similarly, a n minus lambda. If you find the determinant of this matrix along this column, then it will be a11 minus lambda, so a22 minus lambda a n minus lambda, right? So this is your characteristic polynomial. Now what are the root of this polynomial? So lambda equals to a11 a22 a n. So these are the only roots of this polynomial. So these are the only eigenvalues of a, right? So the eigenvalues of a triangular matrix is diagonal entries, right? So all eigenvalues of a triangular matrix are its diagonal entries. Okay. Now, so suppose second property, by using these properties, it's very easy to calculate eigenvalues of many matrices. Now, suppose lambda is an eigenvalue of A. Right. So you can write A minus lambda I determinant is equals to 0. Right. Now, so what you can say about determinant of A minus lambda I transpose? Both have same determinant. This has to be 0. Right. So this will be A transpose minus lambda I transpose is I equals to 0. Right. So lambda has to be an eigenvalue of A transpose. Okay. So this says both A and A transpose have same eigenvalues. Okay. Now suppose you take in place of transpose, you just take conjugate transpose. So let's denote it by AH, or you can denote by A star. So determinant of A minus lambda I. So lambda is an eigenvalue of A, so this determinant will be equals to 0. So determinant of this is equals to A minus lambda I transpose conjugate lambda equals to 0. Now if you simplify this, what you will get A star minus lambda can be a complex number, so lambda bar I equals to 0. So in this case, lambda bar is an eigenvalue of A star. So if A is an eigenvalue of, if lambda is an eigenvalue of A, then lambda bar is an eigenvalue of A star, complex conjugate. Okay. Now suppose you have a symmetric matrix. Symmetric means A equals to A transpose. Okay. Or in real case we say symmetric, or in complex case we say Hermitian. If A equals to A star, right? In both the cases, lambda has to be, where lambda is an eigenvalue of A, then So since A equals to A star, so lambda is an eigenvalue of lambda is an eigenvalue of A, then A bar will be an eigenvalue of A star. So if you write A lambda equals to lambda 1 plus iota lambda 2, and then lambda bar will be lambda 1 minus iota lambda 2. So since both met A and A star have same eigenvalues, so this will be equals to this, and it will be, so lambda 1 lambda will be get cancelled, and lambda 2 will be equals to 0, right? So all eigenvalues are, the imaginary part is 0, so the all eigenvalues are real, right? Now if you take, similarly if you take skew Hermitian, then in this case eigenvalue will be purely imaginary. Or you can get 0. 0 may be an eigenvalue of skew Hermitian matrix. Okay. Now suppose you have a matrix A equals to 1 0 1 1 1 1 0 1 0. Can you tell me what are the eigenvalues of this matrix? You don't need to calculate determinant and all those. You just
So
see.
1 and 0.
So see, what is the sum of first row? Is 2. What is the sum of second row? 2. What is the sum of third row? 2.
2.
So 2 is an eigenvalue of this matrix, right? Now, so sum of all eigenvalues is trace. So what is the trace of this matrix? 2. So
2.
2 plus lambda 2 plus lambda 3 equals to 2. So lambda 2 plus lambda 3 has to be 0, right? And lambda 2 equals to minus lambda 3, right? Now what is the determinant of this matrix?
So 0.
0. So determinant of this matrix A is 0. Now product of all eigenvalues is determinant. So 2 lambda 2 lambda 3 equals to 0. So lambda 2 lambda 3 equals to 0. Now what will be the lambda 2 into lambda 2 equals to minus lambda 3, right? So lambda 3 equals to minus lambda 2, so minus lambda 2 square equals to 0. So lambda 2 has to be 0 and lambda 3 has to be 0. So the possible eigenvalues are 2 0 0, right? Now if you want to calculate by this way, so suppose you have 0 is an eigenvalue, you already know, right? Because determinant is 0. Determinant is 0 means 0 has to be an eigenvalue of A. Now if you calculate A minus 0i, so if you just calculate this matrix, so it will be the same matrix A, 1 1 0 0 1 1 1 1 0, right? Now can you tell me what is the rank of this A minus rank of A?
So 2.
1.
What is the rank of this?
1, I think, sir.
1 or 2?
1. Because non-zero eigenvalue is only 2.
But there is 2 linearly independent rows.
Yeah, so 1 cannot be the rank. So rank is 2, right? Rank cannot be 3, right? Because nullity is you have one 0 is an eigenvalue of this matrix A, right? So rank has to be less than 3. But since you have 0 here, right? So if you two linearly independent rows are there, right? So column, or if you take these two row, these are two linearly independent rows, so rank is 2, right? So in this case nullity is
One.
1, rank nullity theorem. Okay. Okay, now me okay, so let me ask you one more question. Now suppose you have a matrix A and you have a matrix B, right? This matrix is, say, m cross 1, m cross n, right? This matrix is n cross m, right? So AB will be, what will be the order of A into B?
M cross M.
M cross m, right? Now I'm saying lambda is an eigenvalue of A into B. Now what can you say about B into A? B into A will be a matrix of n cross n, square matrix. So we can talk about the eigenvalues of B, right? So what you can say about BA? Now see, lambda is an eigenvalue of A into B. So what you can write, A into B x equals to lambda x for some x non-zero, right? Now if you take lambda not equals to 0, this you consider this case first, lambda not equals to 0, then what you can say about the Bx? Is it 0 or not? If you take lambda not equals to 0, what you can say about Bx? If Bx equals to 0, then what will be AB into x?
Then AB equal to 0, sir.
Bx equals to 0. So A into this 0 will be 0, right? So lambda x equals to 0. X is not 0, so lambda has to be 0. But we are taking lambda non-zero. So this has to be non-zero, right?
Hmm.
So if Bx is non-zero, now if you operate this BA on Bx, right? So what will happen? It will be B A B x, right? Now what is ABX?
0.
What is ABX? Lambda x. B
Lambda
lambda x. So it is equals to lambda B x. This is not 0. So if you take y equals to bx, so BA, if you operate on y, so is equals to lambda y, right? And y is not equals to 0. Although vector is changing, but we are getting same eigenvalue. Now the only problem is if lambda equals to 0, right? So if we take only non-zero eigenvalues, so what we can write from here, all non-zero eigenvalues of AB and BA are same. The only problem is we cannot say anything about the zero eigenvalue, right? Now suppose if you take A as n cross n matrix and B as n cross n matrix, right? Now, so in this case, if you take this particular case, then AB and BA both have exactly same eigenvalues. Both AB and BA have all same eigenvalues. So this is a particular case. If order of A and B are same. But in general, we can say about non-zero eigenvalues. But for zero eigenvalues, we cannot say anything. Okay. So, and someone said linearly independent, something like that. So suppose you have two eigenvalues, lambda 1 and lambda 2, and you have eigenvector x1 and x2. Of course, x1 is not equals to 0, x2 not equals to 0. Now what can you say about x1 and x2 are, what can you say about x1 and x2? So they has to be linearly independent if lambda 1 not equals to lambda 2. So distinct eigenvalues have have linearly independent eigenvectors. Now how will you prove this? Now suppose this is linearly independent. So instead of x or x1 x2, you can write x and y, right? So suppose x and y are linearly dependent. Dependent means x will be equals to alpha times y, right? So x will be, so x1 xn alpha times y1 yn, right? This is the meaning of x and y, n cross n matrix we are taking. N cross, because A is n cross n matrix, and we are doing ax equals to lambda x. So we are taking this n cross 1 matrix. So x means x1 x2 xn, y means y1 y2 yn, right? We are saying x is non-zero, so sum xi is equals to 0, non-zero, because x is not 0, right? And since what is the meaning of this? Meaning of this is x1 is equals to alpha y1, x2 is equals to alpha y2, so and similarly xn equals to alpha yn, right? Now this xi is equals to alpha yi, right? So can yi be 0? No,
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 sir.
because xi is not equals to 0, right?
Yeah, yes, sir.
So both xi and y are non-zero, right? So both xi, all these xi, yi, alpha are non-zero, right? Now since x equals to alpha y, now operate a on both sides, so you will have ax equals to a alpha y, right? So ax equals to alpha, a is scalar, so ay, right? What is ax? Lambda 1 x. What is ay? Lambda 2 y. Both are distinct eigenvalues, right? So a lambda 1 x equals to alpha lambda 2 y, right? So from this, what we will get? For I entry, lambda 1 xi is equals to alpha lambda 2 yi. Okay, so lambda 1 xi is equals to lambda 2 alpha yi. This is true for all I, for all j. So we are talking about this, we are taking this special case where xi is equals to alpha I and both all these three are non-zero. So in this case, this one is equals to this one and both are non-zero. So this will get cancelled. So you will have lambda 1 equals to lambda 2. This is a contradiction because we have taken lambda 1 not equals to lambda 2. Right. So this cannot be happen. Right. So x and y has to be linearly independent. Okay. And if suppose you have a eigenvalue a matrix A n cross n, and suppose lambda 1 lambda n are eigenvalues of A. If all the eigenvalues are positive or non-zero, then it is called positive definite matrix. Okay, and similarly you can calculate eigenvalues. Suppose you have a matrix A, so just calculate A minus P lambda, which is determinant A minus lambda I. So just put this determinant equals to 0, calculate the roots, and roots you will get, and these will be the eigenvalues of A. Right. Now how to calculate eigenvectors? Right. So how will you calculate? Suppose once you have an eigenvalue lambda, right, you calculate A minus lambda I. Right. Suppose take this example where we have taken 1120. I think we took this example 112, 0. Suppose you have this matrix. Now we already know 2 is an eigenvalue for this, right? 2 is an eigenvalue for this, and eigenvector is 1 1. And we have calculated -1 is also an eigenvalue for this matrix. Now we want to calculate eigenvector corresponding to this -1. So what you will do? So just calculate A minus lambda I. So lambda is -1. So A plus I. So it will be 2 1 2 1. Right. Now just calculate null space of this A plus I. So that will be the collection of include. So it will be your E lambda. Right. Now if you remove the 0 vector from this, so that will be your eigenvectors of A plus I. Eigenvector corresponding to the eigenvalue -1. Right. So it will be the whole E lambda, but we are interested only in E. Right. So E will be E lambda. Just remove the 0 vector from this. Right. So how will you calculate? Just 2 1 1 1. So x1 x2, put this null space you want to calculate 0 0. So it will be, so 2x1 plus x2 is equals to 0 2, and x1 plus x2 is equals to 0. So it will be x1 equals to minus x2. So if you put x1 equals to minus x2, you will get minus 2 x2 plus x2 equals to 0. So you will have x2 equals to 0. Something wrong we have done.
So there is 2 instead of 1 in matrices.
Where?
So 2 1 1 1 into x1 x2, there is 1.
Where? Here.
No,
So it
sir,
is a plus I. This is the matrix, right? This is the matrix A, right? So the sum of all rows is 2. This is 2. So 2 is an eigenvalue of this. Now, if you take another one, lambda, so sum of eigenvalues will be trace. So this will be 1. So lambda equals to -1. Right. Now, how will you calculate the eigenvector corresponding to this? You just calculate A minus lambda I. So we want to calculate x such that this has to be equals to 0. Right. So just calculate A minus lambda I. So lambda is -1. So A plus I. Right. So A plus I x equals to 0. Now what is A plus I? So A is this 1 1 2, 0. So A plus I will be 2 1 2 1. Right. So this will be x1
Yes.
x2. Okay, where I did mistake. Okay, here 2. It should be 2. Here I
Uh,
did mistake. Okay, so equals to 0, 0, right? So it will be 2x1 plus x2 equals to 0, right? So 2x1 equals to minus x2. If you take x1 equals to 1, then x2 will be minus 2, right? So your eigenvector will be 1 minus 2. And if you can verify this if x and y are eigenvector of matrix A corresponding to the eigenvalue lambda, then x plus y will be an eigenvector of A corresponding to the same eigenvalue, right? And alpha x for alpha non-zero is also an eigenvector of A corresponding to the same lambda. That's why this E lambda is actually forms a subspace. Okay. Now let me ask you one question. Suppose lambda is an eigenvalue of A and mu is an eigenvalue of B. Now what can you say about this lambda plus mu and A plus B?
So this is the Eisen value for A
Lambda
plus
plus mu will be an eigenvalue of A plus B.
Always?
Don't know, sir.
It may not be. It may not happen that both lambda plus mu, it may not happen. It may not be an eigenvalue of A plus B. This may not be an eigenvalue of A plus B. Okay, but if lambda is an eigenvalue of A, then lambda to the power k will be an eigenvalue of A to the power k. This will hold. And I already told you if lambda is an eigenvalue of A and mu is an eigenvalue of B, and if your A is an m cross n matrix and m cross m matrix, then what can you say about A comma B? Sorry. So lambda is an eigenvalue of AB and lambda is non-zero, then lambda will be an eigenvalue of BA. This will also hold, right? Okay, what about 0? Now suppose 0 is an eigenvalue of AB. What can you say about eigenvalue of BA? Okay, you just take this matrix A equals to 1 0 0 and B equals to 0 0 1. Now what will be A B? This is 1 cross 3. This is 3 cross 1. So your AB will be 1 cross 1 matrix, right? It will be
Yes, sir.
0, sir.
0 0 0.
okay.
The null
You take
matrix.
okay. You take this one 1. This you take this 0. Then it will be
1
1,
0
right?
0.
1 only,
Yes, sir.
right? Okay.
Mm.
What is BA?
BA is first
It will
1
be
0
a
0 and rest of the 0 column.
So BA
A
will
plus
be,
B matrix.
so BA. So just multiply 1 0 0. So 1 0 0. Then 0 0 0 0 0 0. Correct? Correct?
Yes, sir.
Okay. So now 0 is an eigenvalue of BA, isn't it? But 0 is not
Yes.
an eigenvalue of
Hmm.
AB. Now, only eigenvalue of AB is 1. Right? I told you if lambda is non-zero and lambda is an eigenvalue of AB, then lambda has to be a eigenvalue of BA. So the same thing happening here. 1 is an eigenvalue of lambda, BA. 1 is an eigenvalue of BA. Okay. Now, okay. So, okay. Can you give me an example for this one? A plus B. Or just take A equals to 1 0 0, B equals to 0 0 0 minus 1. Now, what are the eigenvalues of A? 1 0.
1
What are the eigenvalues of B?
and 0.
0 minus 1.
0 and minus 1.
Right. What is A plus B?
0.
1
Uh,
0
It's
0
1
minus 1.
0 0 minus 1.
Right. Now, what are the eigenvalues of A plus B? 1 and minus 1. Now, you
1
can take any
minus
number
1.
here. Minus at the place of minus 1, you can take any number. You can take 1 at the place of 1, any number. You take alpha, so eigenvalue will be alpha comma 0. If you take beta, then eigenvalues will be alpha and beta. So if you take 0 0, so 0 is eigenvalue of A, 0 is eigenvalue of B, but 0 plus 0 0. 0 is not an eigenvalue of A plus B. So in addition, it will not hold, and this will always hold. And ABB I have already told you. Okay, let me stop with one more question. Okay, you have just seen AB and BA. If lambda is an eigenvalue of AB, then lambda will has to be an eigenvalue of BA. Right? You have just, if lambda is non-zero. Right? You have just seen this. Now the question is, now suppose lambda algebraic multiplicity of lambda in AB case is suppose some alpha, and algebraic multiplicity of lambda in BA case say beta. Now what you can say about alpha and beta? Are both will be same? So think about it, and we will discuss this maybe in the next session. Okay, with
Sir,
this, let me.
repeat the question one.
The question is, so you have just seen that AB and BA both have same non-zero eigenvalues, right? So suppose this lambda non-zero is an eigenvalue of AB, and the same lambda is an eigenvalue of BA, right? And in AB case, the algebraic multiplicity of lambda is say alpha, and in BA case, algebraic multiplicity of lambda is beta. So what you can say about alpha and beta?
Okay, got it.
So what can you say about this alpha and beta?
Sir, I have another question.
Okay.
You have you have told the in case of addition, the eigenvalue would not be necessary equal to their addition of eigenvalues.
Okay.
Uh, but here one thing happen if lambda is eigenvalue of A, then if we raise to the power A something k, then it will always hold it has eigenvalue lambda raised to the power k. But
Yeah.
if it is given that lambda raised to the power k is the eigenvalue of a raised to the power k, does it
Hmm.
always hold lambda is eigenvalue of a?
No, not necessarily.
Yes. Yeah.
So
Yeah.
for that you need to find an example, but it may
Yes,
not
sir.
hold always.
Yeah. Okay, okay, sir. I am trying to find example.
So it may happen that so if you suppose you have suppose lambda equals to -1 is an eigenvalue of a, right? So now if lambda square will be 1, right? And this
Yes,
is an
sir.
eigenvalue of a square.
Yes.
Now you will see for the eigenvalues of now your question will be whether means what you will take lambda equals to 1 or lambda equals to -1.
Yes, sir. That will be problem.
Yeah, right. And
Mm.
also similarly, suppose you have lambda equals to iota, right? Eigenvalue of a. Now lambda square will be -1. It will be an eigenvalue of a square.
Yeah.
Okay. Or in general, suppose you take a cube, right? So iota cube will be minus iota. Okay, if you just take iota square, a square, right? Now from this again you will have two cases. It may happen that this lambda square is coming from this case, or it may happen that it is coming from this case, or it may happen that both are the eigenvalues of a, right? Suppose you take a matrix A in which
Yes.
this is the only case, right? So one will be an eigenvalue of a square, but this one will be left.
Yeah. Okay, got it.
So one of them will be there, of course, but you can't say like which one will be there. That totally depends on the matrix. Okay. Okay. Any other question?
Yes. And another question is, you have told if we take A and B both the same order n cross n, then we can talk all the eigenvalues of A, B and B are same. But in
Yeah.
case if we take different order of A and B, then we can say non-zero eigenvalues are same, but we can't say about surely in case of zero eigenvalue. But
Hmm.
if we taking order n cross n of both matrix, then we can say all eigenvalues will be same, even if zero is the one of the eigenvalue.
Hmm. Oh, you
And
see this. See. So maybe so you take AB and BA, right? Now suppose lambda is an eigenvalue of AB, right?
yes,
So
sir.
what will happen? AB and BA, right? So from this, what you can say, and suppose order of A and B are same, both are n cross n, right? And zero is an eigenvalue. Non-zero, for non-zero we don't have any issue, right?
Yes, sir.
The question is only for zero.
Hmm.
If zero is an eigenvalue of AB, then what can you say about the nullity of AB
At least one.
greater than equals to 1,
Hmm.
right?
Yes, sir.
Okay. So from this, then you can say about the okay. Suppose AB x is equals to 0 for some x non-zero, right?
Yes. Yes, sir.
So it will be BA. Okay. Now we want a y such that this has to be 0 and y is non-zero, right? Now,
Sir.
so in this case, two things can happen, Right. First one is, it may happen that bx is equals to 0.
Yes.
Okay. It may happen that bx is non-zero.
Yes, sir.
Okay. So if okay, bx is 0, non-zero. Right. So if in this case, if bx equals to 0, right, so what you can say about this bx is, okay, in this case we don't have an issue, right? We just write ba, then bx. You take y as bx. Bx is non-zero,
Yes, sir.
so this will be b a
Yeah.
b.
And Bx is the eigenvector
So this
corresponding
is
to
0.
0. Yes, yes.
This is 0. So b into 0 equals to 0,
0. Yeah. And
right?
we are left with the case Bx is equal
Bx
to if.
equals to 0,
Yes.
right? So in
Yes.
this case, what you can say, and a of, and nullity is, okay, let me see this case, a b a. Now what vector we should choose here so that it will become 0? Bx is 0, so ax. Okay, so if you take this case, okay, let me do in this different way. So in this case, the left case is bx equals to 0, right? So what you can say about the
Nullity of B.
b is not a 0 matrix, so a b. Maybe you need to find this y only. This is the left, so it means you have to make some combination here. So which combination will work here, that we will need to find. So bx,
Sir, it should be left for the next day. We are trying for
sorry,
uh, this is left as exercise. We are trying to, and if not occur, then we will say next class.
okay, it's okay, I will tell
Okay,
you
okay.
this in the next class, which will, I
Okay,
will also
okay,
think
sir.
about it. So this
Yes,
is,
yes,
see, for eigenvectors you have to think about the eigenvectors, like which combination will work,
yes, yes, sir.
right? It is not always easy to identify the eigenvectors, like, means eigenvector you can find out once you have the matrix. Suppose you have a matrix A, you can find eigenvalues, and eigenvector you can find out. But once you have the eigenvector of A, then suppose you have some relation with, of suppose a to the power k, or some a b, something like that. Then for general matrix, you don't, we don't know what are the entries of A, what are the entries of A B. So in general case, so it is very difficult to find out eigenvectors corresponding to the eigenvalues. It is not always easy to find. That's why we generally go for a determinant and all those things.
Yes, sir.
Yeah, even maybe if I'm not wrong, in this case, both will have the same determinant. Determinant of A B equals to determinant of B A. Both they have same order, if I'm not wrong. So in this case, from this also you can figure out A B and B A both have same determinant if order are same. So from that also you can see that if 0 is an eigenvalue of a b, then determinant is 0. So this determinant is also 0. So 0 has to be an eigenvalue of ba. From this also you can see. But for the eigenvector, you have to think little bit.
Yes.
Maybe I will tell you this in the next class.
Okay, okay, sir.
Okay.
Sir, can you cover a minimal polynomial?
Yeah, that I will probably do in the next session. Minimal polynomial and diagonalization and everything I will try to complete in the next session.
Yes, sir.
At least because we need these basic things to go for a minimal polynomial diagonalization and all those things. We need these things.
Okay, sir.
Or if time permits, I will also do some questions from previous year papers.
Okay, sir.
Okay.
I hope there are no more queries left. Thank you so much for such an engaging and wonderful session, Akshay sir.
Thank you. So can I leave the meeting?
Participants, please note that next session will be on Thursday, 13th November 2025 from 6 p.m. to 7 p.m. as per the schedule. So let us meet there. Goodbye.
Thank you.
Thank you, sir.